Great. Okay, so we are recording the meeting. Let's start. Good morning or good evening to all, and welcome to the Data-Driven Community virtual meetings. A few words about the Data-Driven Community. As you can notice at our website, we are managing two branches of activity. If you scroll down the page, you can see the upcoming events. On the right side of the page, you can check the upcoming weekly meetings of the Cloud Data-Driven User Group, like today. The second branch of activity we run is an annual conference called Future Data-Driven Summit. Don't delay getting your early registration completed. I will give you the link in the chat after I will finish the introduction and the speaker will start the session. We are thinking about doing some swags for early registration, so it cannot be bad. If you will register now, you will get a few update before the meeting. The conference itself is on September 25. But as I said, go register now. Please feel free to use the chat during the meeting today for questions and discussions as well. This is a user group meeting, not a conference. We are not strict about the time. We can be a bit flexible, so you can feel free to discuss between yourself as well. You are also welcome to use the reactions. It doesn't interfere with the course of the meeting. Personally, I love it a lot. If you hear something you love, like, or you just want to clap hands virtually, you can do it using the reactions. You are more than welcome to contact any of the community board members if you have any suggestion or question, or if you want to speak in one of the upcoming meeting. You can notice on the left, Jen Joseph is the founder of the community and the co-admin. Anna Weekly is the second co-admin. My name is Ronen Arieli. I'm from Israel. I work as a senior consultant in the field of data platforms and architecture of enterprise level system. I'm the third co-admin of the data-driven community, and I will be hosting the session today. So those are the board members, and our guest speaker for today is Alex Merced. Alex is a senior tech evangelist at Dremio, and he is a very known influencer in the data platform community. You can go to his LinkedIn. He has a lot of followers, so this say a lot. Alex, you are welcome to share your screen and take control. Maybe add some word about yourself when you start.
Okay. Hey, everybody. My name is Alex Merced. I'm a senior tech evangelist at Dremio, and welcome to today's presentation. Now, before I get started, I always like to give opportunity for anyone who wants to download the slides for the presentation to scan this QR code. Now, when you scan this QR code, it'll take you to a folder with not just the slides for this presentation, but for many of the presentations that I regularly deliver. So lots of slides, a lot of content to go look around and enjoy there. So I'll leave that up there for like another few seconds. And yeah, now we'll begin with our show. Okay, again, we're going to be doing a presentation called Open Source in the Lakehouse. So basically, my goal today is to talk about many different really cool open source projects and how they relate to the data lakehouse and how they enable data lakehouse patterns. And as I mentioned before, I'm Alex Merced. I'm a senior tech evangelist at Dremio. I've worked in the web and data spaces as a developer for companies like Genet Systems, Crossfield Digital, CampusGuard, General Assembly. I'm one of the co-authors of O'Reilly's recent book, Apache Iceberg, The Definitive Guide. And I've spoken at many events such as Data Council, Data Day Texas, and many more, and in the host of several podcasts, which we'll show you in a moment. Now, when it comes to Apache Iceberg, the definitive guide, you are able to get a free copy. That's at this QR code right here. And basically there you can just get a free PDF of the whole entire final manuscript. And so for those of you interested in Apache Iceberg in particular, that is available to you. Along with that, as I mentioned, I'm the host of several different podcasts, which are all available on iTunes and Spotify. That URL right there, bio.alexmerced.com, will just give you a quick link to all of those, plus my social, all of that. So anywhere you'd want to follow me, you can find it there. And one last announcement is that we are going to be doing an Apache Iceberg crash course. So this will be 10 sessions of just going through like what is Apache Iceberg, hands-on exercises with Apache Iceberg, and so forth. And to register for that will be this link. If you are watching this presentation after the fact, so after October 29th, this link will still also get you to the on-demand content for those live sessions. But with that, no further ado, let's get on to our feature presentation and start talking about open source and the Lakehouse. And we're going to start off by talking about...
Just before you start, we have a lot of people that just joined. I just want to say it's legally as well. We are recording this session, so just know that everything is recorded. The chat is not recorded usually, but we will publish the recording afterward.
That's right. So make sure if you missed this, you can watch the recording. And if you're watching the recording, welcome to the show. Now, let's continue on with what is a data lakehouse. So to understand what a data lakehouse is, we need to kind of talk about what came before data lakehouses, sort of like this, sort of the traditional way we sort of would move data. So traditionally, we would have sort of our different data sources. We would then ETL that data into a data lake, and then that data would then get moved into a proprietary data warehouse. And that data warehouse really abstracted several layers of, well, things that would help us manage our data. So such as, how do we store that data? Abstract it away. How do we recognize each individual table and what format is that data stored in? All that abstracted away. Again, as a user of the data warehouse, I don't have to see these things. I don't care about these things. And also, how are those queries processed? So what is like the query engine that parses my SQL, creates a query plan, and then executes that query plan? All abstracted away. Now, this is all well and good. Problem is, the use cases for data have expanded greatly, okay? And they're expanding more so every day. On top of it, the amount of data is expanding every day. So putting all of our data in data warehouses starts getting more and more expensive for those storage costs. But also, no platform really has every feature you need for every use case. So the need to use multiple platforms is becoming more and more a necessity. So you end up having this problem where you have the growing cost of storage and compute within some of these platforms, proprietary components. So in that case, if I do want to use multiple platforms for different use cases, it results in me having to copy my data, which results in sort of consistency issues, all sorts of different types of problems. And then again, as you have all these copies of problems, you end up with like data drift, model drift, as you try to keep all these copies in sync. So to try to address a lot of these problems, we're starting to move towards data lakehouse architecture. Even most data warehouse platforms are sort of moving and enabling this sort of data lakehouse architecture, where basically instead of moving your data into the data warehouse, you basically have sort of a single source of truth, a single copy of your data in your data lake organized into different tables through table formats. So this is like Apache Iceberg, Delta Lake, Apache Hoodie. And then those tables can then be operated on by different tools, including data warehouse platforms and other query engines that have focused on data lakes, like Dremio, like Apache Spark, and several other different platforms that are able to interact with these data lake table formats. Okay, and you end up having the data lakehouse, basically, where you're treating your data lake as a data warehouse, allowing you to use multiple platforms, multiple tools, depending on your use case, and allowing you to have one copy of data, minimizing your storage costs at a lower cost per unit storage. Okay, and the benefits there, again, more inexpensive. Basically, you're going to get that data warehouse-like functionality thanks to formats like Apache Iceberg. And again, you'll be able to use a variety of tools. So there's different pieces, because essentially what a data lakehouse is, it's a deconstructed data warehouse. It's you taking everything that was abstracted away in a data warehouse and implementing them separately. So there's different layers of what you need to implement to kind of get back to that functionality, such as a storage layer. So this could be like cloud or on-prem object storage or Hadoop, but you need somewhere to store the actual data files. But ideally, you're going to want, especially your structured data, to be kind of in some sort of format that's optimized for analytics, such as Apache Parquet. Okay, so an open binary columnar format. We'll get into more detail later on in this presentation. You're going to want all those Parquet files because one data set might be 100 Parquet files, 1,000 Parquet files, 10,000 Parquet files. You want to be able to group those Parquet files into tables. So that's where a table format like Apache Iceberg comes in. That allows us to kind of create a canonical list of which files belong to what tables and which version of that table. But we also need to be able to discover those tables. So we need to have a catalog of our tables, whether that's Project Nessie, AWS Glue, Hive, now like Unity Catalog. All these tools can be used to sort of say, hey, here's our list of tables that we have, so that way tools can discover them. And then we need some sort of engine to write SQL or Python against that then takes that code and then creates a query plan and processes it. So these could be things like Dremio, but this could also be like Trino, Presto, Snowflake, Databricks. All of them offer different sort of query processing tools that work with these formats. Okay, and then just show you sort of one sort of like in practice implementation, like one way this could look like as you choose these different layers. I might choose object storage. I might choose the file format as Apache Parquet, and I might specifically choose Apache Iceberg. Now, each format does have their pros and cons. Pros of Apache Iceberg would be like the ACID transactions, time travel, the ability to evolve my partitions, to be able to evolve my schema, hidden partitioning, which I'll get into more later on, but that's a feature that makes partitioning easier for the data engineer and easier for the data analyst, and support for multiple formats. And then for catalog, I could use a catalog like Nessie that's going to enable things like Git-like functionality, allow me to branch my catalog, to be able to merge my catalog, to do things like multi-table transactions, isolate transactions, etc. Okay? Or use an engine like Dremio that has an easy, intuitive UI, a semantic layer for organizing all my business metrics, and then very high performance. Okay, and that connects directly to tools like Power BI and Tableau pretty easily. Okay, so we have a variety of different ways we could implement the data lakehouse, but this is sort of one example. Now, why does that open? Because before I'm talking about open source, and so I'm talking about all these different open source technologies. What does the open really, or why does it matter? One, for innovation, because when you have something that's open source, you have a lot of people who can contribute to it, and that's going to create innovation because people can bring all sorts of different ideas from the inside and the outside. On top of it, you might have competing open source projects like you do with the table formats. I would say Apache Hoodie, Delta Lake, and Iceberg are all better projects because the other projects exist, pushing each other to innovate and to be actively developed. So you have that sort of innovation that comes from the competition, even within open source, along with the competition that exists or the innovation that exists from just internally from the open source community. Ecosystem. Now, I'd say this is particularly important for projects that represent standards. So these are things like Apache Parquet that represents a standard that we all want to use for storing our data, or Apache Iceberg, a standard for how we organize that data as recognizable tables in our data lake, or Apache Arrow, a standard for how we represent that data in memory. Well, those standards you really want to be as open as possible because you're trying to build an ecosystem around them. Okay, and if you want to not just people to use the thing, but you want people to build their businesses using the thing, you want to make sure that it's sort of undo of sort of like too much concentrated commercial interest. So that way people are comfortable and feel certainty that there isn't some other entity that can kind of pull the rug under them as they embrace and build around these platforms. So ecosystem and cost. Oftentimes open source can really help. That sort of openness can really allow there to be pressure to optimize sort of costs to the consumer. Okay, but at the end of the day, that's why open is important. But what does it mean to be open? Because oftentimes we think of open just as the ability to see the code. We're like, oh, okay, I can see the code, so that's open source. And yes, that is. But there are several layers of openness, which actually I talk about in more detail in a recent article I published on Medium, Shades of Open Source. But there's also the idea of like open and transparent contributions. Like yes, I can see all the code, but are all the contributions made in a way that I can see who's making the contributions and what they're contributing? Okay, because there's some repos that where they have like a proprietary version of the repo, and what they'll do is a lot of activity, a lot of individual commits and contributions happen there, and then what they'll do is they'll then open source that code as one sort of big pull request back into the open repo. So you can't granularly see who's contributing those individual bits of code. Really kind of get an idea of like, hey, where is sort of the gravity of work being done, and what is the influence in the project or the direction of the project. And then also open and transparent governance, okay, in the sense that when you have a board or a body that governs the body, like are they made up of people from several different sort of different institutions? So that way, again, there's not sort of one sort of party sort of controlling the direction of the project. And again, the reason why that's important is one, if one party really has that kind of control, then generally what gets developed, what pull requests get merged are oftentimes going to be in the favor of that one institution or based on the plan of that one institution. But also that institution can then change things in ways that then can be the word I can what's the best way to use this, basically not into the benefit of other parties who might be using that project. So again, that certainty that you're not going to have the rug pulled out under you is a benefit of having sort of these openly governed, diversely governed projects. So, and that's one of the beautiful things when you see that word Apache, because the Apache Foundation, the Apache Software Foundation, has several different rules for being an Apache project, as far as like active development, active community, but also diverse governance. Like you can't have a concentration by any commercial interest in what's referred to as the PMC, okay, the committee that governs each individual Apache project. So this kind of helps ensure that these projects, one, last a long time, but also that the word Apache, when you see it's an Apache project, it gives you that certainty that this is sort of a independently open project, such as Apache Parquet. And Apache Parquet goes a long way in enabling data lakehouses, because one of the problems before you had like things like Apache Parquet or ORC, and still to this day we store a lot of our data in like CSV and JSON files in our data lake. The problem with that is that CSV and JSON files, because they're text-based files, they take up more space. They also take longer to parse and then query. So you don't get the same kind of performance as you would in a data warehouse. So thus you have this sort of pattern where people dump a lot of data in JSON and CSV, then move that data into a data warehouse for that performance analytics, but then you get all those costs. But Apache Parquet gives us a way to store data directly in our data lake or any storage system that's going to be optimized for better performance. And it does this in a few different ways. One is binary. So basically, it's going to be encoded in a way it's going to allow for maximum compression, faster reading, but also it breaks down that data into different. So while it's still columnar data, so you're technically, each column is a separate data structure, like a data frame. But there's always like groups of rows. So there's like chunks of rows called row groups, and each row group is going to have its own metadata. So this sort of structure of breaking down the data into different row groups offers a couple different benefits. So if I'm a query engine like Dremio, I can open up, like, let's say, a gigabyte Parquet file, look at the different row groups, and do what's called predicate pushdown, where I sit there and say, hey, you know what? I'm looking for users between the age of 20 and 30. And then I can look for that column and see the metadata for that column for that row group and say, hey, does this particular row group have users between 20 and 30? Nope, I can just skip reading that row group. So in that case, I don't have to read the full gigabyte of data because I can identify which chunks of that file actually have relevant data. On top of that, having the data split up into row groups makes it much easier to do parallel processing, because I can then send those different row groups to different nodes on a massively parallel system. The systems like Dremio, Spark, Flink, that generally are processed across multiple computers as one big system. Okay, so again, Apache Parquet allows us to store that data in a way that enables processing at those much higher speeds. But again, as I mentioned earlier, we're not talking about just 1 gig data sets. We're talking about sometimes terabyte data sets, petabyte sized data sets. So that means there's going to be more than one Parquet file. One Parquet file is not going to do the job. So you might have a data set that is hundreds of Parquet files, thousands of Parquet files, and tens of thousands of Parquet files. So while one Parquet file is very well aware of the data inside of it, a Parquet file is not aware of the other Parquet files and the data inside those Parquet files. So then you need some sort of other layer on top of that that is aware of the full picture of like all the files in the data set and the statistics of the files in that data set. So that way you can more efficiently scan that data set. And this is where table formats like Apache Iceberg come into play. So essentially what Apache Iceberg does, it provides a sort of metadata layer. So again, at the end of the day, your data is still in Parquet files, but with the metadata layer, I'm able to identify, hey, these 1,000 files, these 10,000 files are part of the table and have the stats of those files in one place. So that way I don't have to go look through each file to determine whether I should scan it or not. I can use that metadata, only have to look through a few files and determine, hey, out of the 1,000 files in this table, I really only need to scan these 30, resulting in a much faster scan. Okay, which also, and then things like partitioning, schema, all this stuff's in the metadata that enables it, an engine to do a lot more of those operations much earlier at a higher level without scanning as many files and doing as many folder listing operations. So basically, Apache Iceberg specifically does it through a sort of a 3-tier metadata layer. So there's 3 types of metadata. There's the high-level metadata files. These are generally like defining the table. So like, hey, here's the table, here's where it's physically located, here's the schema, here's the partitioning. Basically defines the table. So that's usually like a JSON file. But then what's going to happen is that there's going to be chunks or groups of files. So each group of files is referred to as a manifest. So that's this right here. So, and then generally these, like each manifest might represent like a partition. So hey, here's all the files in this partition. It may or may not, depending on how the writer writes it. But then what happens is that a single snapshot of the table might be made up of many of these manifests. So then there's this middle layer called the manifest list that lists which manifests belong to a particular snapshot of the table. So essentially, something like Dremio could go see the metadata file, realize, hey, look, this table has 2 snapshots. And then depending on which snapshot of the table that I want to scan, it'll send me to the manifest list for that particular snapshot. And from there, I'm going to have rolled up statistics for each manifest. So essentially, it'll be like aggregated statistics across all the files in that manifest that I can then use to say, hey, does this manifest even make sense to look at? And I can skip entire chunks of files based on one record. Because I can be like, hey, you know what? In this manifest, there are no files that have any records with a user between 20 and 30. And I can just skip an entire chunks of files. But then once I've determined which manifest to look at, I can then go down a layer to the manifest and see the statistics for each file and start eliminating individual files and saying, okay, this file doesn't have anybody I need. This file doesn't have anybody I need. And then I've now narrowed it down to the narrowest number of files. And now an engine like Dremio can then go read those individual files, parse out those row groups, and continuing predicate pushdown at the file level, giving you sort of maximum performance because you're skipping files that don't need to be scanned at all. So that's essentially like the benefit of these formats. They give you this level of information that allows engines to much more plan how to scan those files in a much more efficient way. But not only that, because of the structure of the metadata, you get a lot of other benefits. You get concurrent reads and writes. So table formats typically have some sort of mechanism for basically keep watching out for concurrency. So usually it's done through optimistic concurrency control. So typically what happens is that just means that basically if you have 2 writers, both parties will write, but whichever writer finishes first wins, and then the other writer would have to then reattempt it. And there'd be some sort of mechanism for identifying that. So basically Iceberg does that. In that case, you won't have any concurrency issues when you have multiple writers. You have hidden partitioning, which I'll give sort of the high view of this because it gets a little deep. But essentially, if we go back to the past, so before the table formats, before Delta, before Iceberg, before Hoodie, you had Hive. And with Hive, you partition truly based on the raw value of a particular column. You say, hey, let's split up this table based on the value of the date. But the problem is if you did it based on date, date values are like nanoseconds, seconds. So you'd create like a separate folder and separate files for every individual timestamp. That would not be practical. You'd end up with too many small files for very slow scans. So typically what you would do is that you'd have to choose a granularity. You'd say, hey, I want to partition the table by month. So then when you ingest the data, you would actually have to sit there and create a column called month, and then you'd have to translate that timestamp value into a month value, and that would be a separate column stored in all the files, and you'd partition based on that value. So that made it a little more work for the data engineer when ingesting, but also made it more work for the analyst when querying. Because now saying, hey, give me data between this timestamp A and timestamp B isn't good enough. For me to benefit from that split up, I'd actually have to add a separate predicate that says, also give me any records between this month and that month. And if I didn't have both, I didn't really get accomplished the query that I wanted to accomplish. With hidden partitioning, you don't have to do that. You can actually specify in the metadata the relationship of a transformation of the value. So I could actually say in the metadata, transform it based on the month value of this timestamp. So in that case, your data files will only have the timestamp column. You don't need to have another column. Instead, it's all kind of figured out during the metadata reading process. So those transformed values are stored in the metadata and used to evaluate which files to scan during the metadata. So basically, the engineer doesn't have to worry about making another column, and the analyst doesn't have to worry about adding an additional predicate to their queries, making the whole process easier. You have rich table evolution, so you can evolve the schema. More uniquely, Iceberg can evolve partitions, so you can actually change the way the table is partitioned without having to rewrite the whole table, which is a big deal, because last thing you want to do is rewrite a petabyte-sized table if you can avoid it. So that's a pretty nice feature. So you get a lot of really good features. Okay, and because of that, and you also have ways to kind of make that table more flexible for better performance, whether being able to flexibly choose when to do copy on write strategies or merge on read strategies, where basically you don't rewrite entire data files at write time. So you have all this flexibility to kind of create sort of optimal sort of patterns to scan very large tables, very large data sets very efficiently. And Apache Iceberg, again, with that Apache prefix, you have that sort of open, community-driven standard to do that. So just to recap so far, we have Apache Parquet that gives us a really fast file format to store the data in, and then we can organize those files into a recognizable table thanks to Apache Iceberg. But if I'm Dremio, once I've read the table and I've read the individual Parquet files, well, I can actually process the query, and I have to load that data into memory, and I got to load it into some sort of in-memory representation, and that's where Apache Arrow comes in. So essentially what Apache Arrow is once I read that Parquet file and I load up all those records into the memory of all the executing nodes, how do I represent that in memory? Well, Arrow. And actually Arrow has its start. Basically, two people were trying to solve this problem at the same time. So you had Wes McKinney, who famous for libraries like Pandas, and you had Jacques Nadeau from Dremio, also trying to solve that issue for the Dremio query engine at the time of what's the best way to represent memory in the data in memory. So they worked together. So technically part of what Apache Arrow was the in-memory format for Dremio back in the day. And it evolved into this now pivotal open source project that's now really underpinning achieving performance in query execution. Not just in Dremio, even though it's a key part of Dremio, but you're starting to see all these sort of open source engines like Data Fusion. There's a project called Apache Comet that's sort of basically creating a replacement for Spark. So that way you have Arrow-based execution in Spark. It's becoming sort of a really big deal as far as how do we execute queries and execute them fast. But essentially what it is, it's a way to represent data in memory in a columnar way. But the more importantly, it's not that people didn't do it before. Like different query engines and data warehouses would represent data column in a columnar way, but everyone did it differently. Okay, and the problem was every tool had to come up with their own way of serializing and deserializing that data. Okay, now since you have these open standards, you know, Apache Arrow, Apache Parquet, they all talk to each other. So oftentimes like the steps, the amount of work to load up a Parquet file into Arrow is very minimal, allowing you to read that file format very quickly and have it in memory really quickly, then move it in quickly. And on top of it, Apache Arrow has a transfer protocol, which we'll talk about in a moment. So now I can send that data without having to serialize it and deserialize it between different machines over the network, basically really removing a lot of these, what's the word I'm looking for? Basically these blockages of performance, these bottlenecks, that's the word I was looking for, that would slow down performance. And the cool thing about the Apache Arrow project is that this format, they've made a lot of effort to make sure that you can use it no matter what language you write your tool in. So if you're writing a tool in C++, you're writing the tool in Rust, you're writing the tool in Golang, they have a Rust library for that language. So that way you can make sure that your tools support Rust. Okay, it's become rapidly adopted. It's pretty much everywhere in the data space nowadays. And you can see like it's just skyrocketing in downloads, and is being used by everywhere to speed up performance. It's a pretty cool thing. But again, I mentioned there's a transfer protocol, and that's Arrow Flight. And what Arrow Flight does is that it's like JDBC ODBC. So JDBC ODBC is standard for transferring data from database systems forever. The thing about JDBC and ODBC is that it transfers the data in a row-based format. And generally, when you're doing analytical type computations, you want to in a columnar format. So what would happen is JDBC, ODBC, you would take the data, turn it to row-based to transfer it, and then have to convert it back to columnar on the other end. And that would create some slowdown. Okay, so essentially what this does, it creates a framework for a server. So let's say Dremio would implement an Arrow Flight server within their platform. And then that server has the ability to receive Apache Arrow objects over the wire through a gRPC framework. And then you would have clients that would implement that gRPC framework on the client side and be able to send and receive Arrow Flight or Arrow objects from events. So in that case, it just stays in the same format from end to end, and you're not having to recalculate the object or serialize the object. Okay, and that made life a lot easier. Okay, and the way it's designed is actually it's column oriented, of course, but also it's set up in a way that you can break up the data. So for example, if I were to say, hey, I send the instruction saying, execute this query for me in Arrow Flight, that query might be broken up and over across several different nodes. And basically what it does factor in the ability to go collect bits of that data from several different machines, which allows me to sort of parallelize the calculation and to parallelize the receiving of that data. Again, it's probably still early days as far as really fully taking advantage of that, but it's designed to enable that. The way the protocol works allows you to kind of sit there and say, okay, hey, here's my ticket for the results, and then I can go back and then request to those individual nodes each piece of the results set. So, which again allows the results to be parallelly computed and allows me to retrieve them in a parallel way, which can allow all sorts of different optimizations. And again, this really is a matters at high volume amounts. So here you can see some examples where we're comparing ODBC versus Flight. So when you're talking about like 2,000 records, there's a benefit, but not like a tremendous benefit. But when you start getting to like 5 million records, 1 billion records, it's a dramatic difference in the amount of time it'll take to send that data from point A to point B. Okay, again, everyone's embracing Arrow. Snowflake has added an Apache Arrow Flight endpoint, etc. And so again, we already talked about this Arrow Flight stuff. So again, it's just a way to send that data. But also what they did is they created an SQL interface on top of that protocol, and that's called Arrow Flight SQL. So it's just essentially another layer of abstraction that allows you to send SQL that will then underneath the hood turn into these Apache Arrow Flight requests. So that way you can just write SQL and it just gets executed. Okay. But I'm going to move forward from that. And another really exciting thing is that it's like incumbent on each platform to basically implement Arrow Flight. So basically Dremio has an Arrow Flight endpoint, Snowflake has an Arrow Flight endpoint, InfluxDB has an Arrow Flight endpoint. So they've implemented the server side of Arrow Flight in each of their platforms. So then someone who wants to communicate with those tools has to use a client. Okay, but most people are used to using ODBC and JDBC. Okay, they love, because what they've been using forever. So what Dremio did and contributed to the open source community is they created an ODBC and JDBC Aeroflight driver. So basically, it's an ODBC or JDBC driver you can install that allows you to connect to Aeroflight supporting tools without having to just doing it the way you're used to. So in that case, you can have that one driver. So that one ODBC driver, that one JDBC driver would work for Snowflake, for Dremio, for InfluxDB. So the idea being, hey, there's one driver that allows you to connect to several different tools instead of having to install another driver for each tool. That's the beauty of having a standard. And also a standard server client protocol. And then even further, over the last couple of years, the Apache Arrow project has created a new protocol called ADBC, okay, which is Arrow database connectivity. Okay, and essentially this is like a replacement for JDBC, ODBC. The difference is that it transfers data. It's built to transfer data as a columnar format. Now, not every tool uses Arrow. Not every tool has an Aeroflight endpoint. So ADBC facilitates for that, where it's like JDBC and ODBC, where you have different drivers. So there is an Aeroflight driver for ADBC that allows you to connect to all the Aeroflight things. But for things that aren't Aeroflight, they can come up with their own custom columnar drivers that work with this ADBC protocol. So basically, it helps facilitate other types of columnar formats to have that faster transfer as well. So the Arrow project is all about sort of, again, the transfer and in-memory representation of data. So that way you can process it faster. Okay, which is why you're starting to see some of the crazy performance numbers you see from Dremio, Data Fusion. There's a GPU-based engine called Theseus. There's all these different sort of tools that are really leveraging sort of this protocol. Okay, and the final project that I'll talk about is Project Nessie. So this is probably the newest of the 4 projects. But again, to lay everything out again, Apache Parquet allows us to store our data files. Apache Iceberg allows us to recognize those files as different tables, and then Apache Arrow allowed us to process queries on that data really quickly. But one thing we also have to do is we need to make sure that our tables are discoverable by different tools, especially our Iceberg tables. This is usually done through the catalog mechanism. Project Nessie is specifically a catalog, was originally made for Apache Iceberg tables. It doesn't have to only be for Apache Iceberg tables. It has a very flexible architecture. But essentially, taking a look at sort of like the evolution of things, we take a look at historical evolution. We start off with like data lakes, and the big deal was Apache Parquet. It's like, hey, look, we have these faster files that we can scan in our data lake now. And then we started moving to the data lakehouse. We had able table formats. Say, hey, now we can treat these files like actual database tables on our data lake. So then sort of like the next evolution is like this concept of data as code, where we start introducing sort of like Git-like functionalities on the data lake at the catalog level. So the ability to isolate workloads, the ability to version control our data lakehouse, the ability to govern our lakehouse in sort of a portable way. And that's essentially what sort of the problem that Nessie is trying to solve. So kind of recap, again, when you take a look at that evolution, you have your columnar file formats, you have your table formats, but then you throw in that data as code catalog. Now you're able to, it's not just one tool, it's not just Dremio that allows you to do versioning, but you can take that same catalog and use it with Spark, you can use it with Flink, you can use it with Snowflake, Trino, Athena, and get those benefits of being able to do branches of your catalog, tags of your catalog, all the kind of same things you would benefit from in the Git repo, but on your data at a more table level. Okay, and the way this would work is that here you have your object storage, okay, and every time you update an Iceberg table keeps track of different snapshots. Okay, so you have, say, snapshot 1, snapshot 2 of that individual table. But what Nessie does is that it captures the pictures of all of these, like what's the current state of each table at a catalog level. So you can see here, like on this commit, both tables, table 1 and table 2, are both at version 1. So that's like the first commit. Then we update table 1. So now we have a new commit in Nessie, and now the new listing of tables says table 1 at version 2, table 2 at version 1. And then we update table 2. Now the newest commit on Nessie. And that makes it very lightweight because it's not capturing the changes to all your files. It's just capturing the changes of the table versions. So it makes it really lightweight so it can handle really high throughput. when you're having lots of frequent changes to your tables. And then you can then time travel the entire catalog. So in this case, if I wanted to go back to the beginning of both tables, instead of me having to time travel each table individually using Iceberg, I can use Nessie to just go back and scan my Lakehouse at this commit, which will look at the original versions of both tables. So it allows me these sort of multi-table Git-like semantics, whether it's branching, merging, tagging, it all happens at a catalog multi-table level. And it allows these semantics to exist with whatever tool you use, whether it's Dremio, Spark, AWS, whatever tool you use. And that's the beauty of it. Everything here is all about trying to build sort of portable, open platforms, and then you can swap out the tool you need on top depending on your use case. Thus the whole sort of data lakehouse stream. Okay, and again, we have that whole data as code. So the ability to isolate changes to your code or changes to your data. So I can create a branch, make changes to multiple tables, but none of those changes are published until I merge the branch. Okay, I have version control, so I can go back and roll back to a previous commit if something goes wrong. So it makes disaster recovery really easy. And governance. Okay, Nessie has the ability to create certain governance rules that are portable. So that way, hey, if this particular user connects, they can only access these namespaces, or they can't access those. And you can create portable governance rules to make sure that people can only access what they're supposed to access, regardless of which tool they're using. Okay, and this also changes the paradigm of how we do transactions a little bit differently. Because in a data warehouse, what you would do is generally you would do these multi-table transactions in one session. It would be one user who writes one query. And essentially it would look something like this. It would be like a begin transaction, and then you'd have a bunch of SQL in between, and then you would commit that transaction. And yes, all of that would happen simultaneously, and you'd have that multi-table transaction, but you still have to do it at like one time. Now, with Nessie, it could happen across multiple sessions, multiple users, multiple engines and services. So essentially what would happen is that I would create a branch, and then different operations can happen. So we might have some Kafka ingestion occurring on that branch. We might have some ingestion from a database occurring on that branch. We do some transformations from Spark on that branch. We do some additional transformations from Dremio on that branch. So these are all separate transactions being done by different people and different tools, and none of them are published until we finally eventually merge that branch. So it really gives you a flexibility in sort of what the pattern is between the beginning and the end, and when you publish these things, which is pretty cool. And again, Nessie works with all engines, and this goes even further now because recently Nessie adopted the Iceberg REST catalog spec, which is a specification for Iceberg catalogs, really expanding the number of tools that it works with. So Nessie's really expanded its reach just in the last few weeks. But beforehand, you could already use it with Dremio, Apache Spark, Apache Flink, Presto, Trino, all the open source tools. But now you can pretty much use it with pretty much anywhere that you can use Iceberg. Okay. But yeah, so bottom line is that open source technologies have really made it possible to create sort of an open data warehouse like platform on our data lakes that allows us to use whatever data lake we like, whether it's ADLS, S3, Google Cloud, allow us to use the tools that we like, whether we're looking to use like a Fabric data lake house, or we're using whatever sort of machination we want, we can do that. And a lot of that is because these open technologies really underpin the ability to replicate that, that open environment. And yeah, that's the end of the presentation. Again, I will be doing a 10-part Apache Iceberg crash course across, that's going to be going on throughout these dates. July 11th, first one's July 11th, the last one's October 29th. So if you want to register for those, there's a QR code for it. But what I'm going to do now is put on my glasses so that way I can see whether anyone has any questions in the chat. So let's take a look at the chat.
Yes, I've just saw it and plan to tell you if you're watching the chat so you can get it directly.
Cool. So let's see here. Let's scroll to the top so we can start first in, first out. Okay, use the following link to register. Yep. Okay. Hi, Alex. We use Hive as our data warehouse and metadata storage for many years, and Iceberg is relatively new to me. Could you talk about the difference of the two systems in real production scenario? I've learned that Iceberg supports asset operations and many more metadata management efficiencies. So I'm wondering whether it's tangible to migrate from Hive. Iceberg is actually really built to make the migration from Hive tables to Iceberg tables really easy, because you can actually use your Hive metastore as your Iceberg catalog. So you don't necessarily have to toss everything out. You can start saying, hey, certain tables are Iceberg tables going forward, and see how that goes. But as far as like the mechanical differences, the way Hive worked is that basically the Hive metastore would store, okay, hey, table A is in this directory, and the partitions for table A are in these subdirectories. And that would be stored in the metastore, allowing an engine like Dremio to know, okay, hey, where is the table in the partitions? But that's as granular as it got. So if I were to like update a particular partition, if I wanted to update one record atomically, I would have to swap out the entire partition. So essentially what would happen is I would rewrite that partition with the update to one record, and then I would swap out the folder reference in the metastore. So it would create, it was like slower to do those more granular updates if you wanted to do them atomically. And you couldn't really update multiple partitions atomically because of that mechanism, the way the mechanism was. So you had a lot of these bottlenecks. That was actually the reason why they created Iceberg, because they were using Hive at Netflix, and they were running into all these different bottlenecks. And they're like, okay, hey, you need to come up with something that kind of overcomes this. And this was the solution they came up with at Netflix, that eventually became the open source Apache Iceberg, created by Ryan Blue and Daniel Weeks, who were the creators of a company called Tabular that just recently got bought by Databricks. Big news last few weeks ago. Basically, the efficiency is different. Is that in Iceberg, what the Hive metastore would do is would have that reference, because the way Iceberg, if I go back to like the architectural diagram in the beginning, let me just go back to that. But what happens is that the catalog only contains a reference to the most up-to-date metadata file for that Iceberg table, and then everything else is read through the metadata tree. So then what happens is that with Hive, that reference would just be stored in Hive. So instead of saying, hey, this table's in this folder, it would say the newest metadata is in this file location. So essentially this Iceberg catalog, that would be your Hive metastore, and it would store references saying, hey, like this table, the file location on your Hadoop or on your S3 or on your ADLS is here, and then the engine really operates off of this. And this here has lists of individual files instead of a directory. So the engine doesn't have to go like list, hey, what are all the files in this folder to read the table? And it can identify earlier what it doesn't need to scan for a much faster querying. So that metadata really, what the Hive has to track is much less, and the granularity at which the engine can use for planning is much more. I hope that kind of gives you somewhat of a higher level to that. That answers your question. Let's see here. Yeah, I think that should. But as far as migrating, it should be pretty easy, because you don't have to create a new catalog. You can just use your existing Hive metastore, and Hive and Iceberg tables can coexist. Cool. And I'll give it another moment to see if there's any other questions. But again, if anyone wants to download the slides, so let me go back to the beginning where that slide QR code was. I'll put that up there for anyone who wants to download those slides. And again, I just want to say thank you guys for sticking with me throughout this hour to hear about all these really cool open source technologies. I talk a lot. So again, make sure to follow me on LinkedIn or on Twitter to find out about where I'm talking next. Actually, I'll be talking this evening at the Tampa Bay Data Engineering meetup about tonight. I'm talking about the semantic layer. So if you want to hear about that, come join me again later on in the afternoon. But yeah, no, thank you so much.
Thanks a lot, and thanks to everyone that joined us. You can use this QR code in order to find the community website, but you have all the links at the chat, so it is faster to take it from there. I remind you, join us at the Future Data Driven Summit, which is the big yearly event. It is organized by several communities together, several user groups, and we are all collaborate together into one yearly conference, and we have the weekly events you can all get in the website. So again, thanks a lot, and a great session, Alex. Thanks.
Thank you very much for having me.
Okay, I will close the meeting unless someone have more questions. So we'll see you next week. Bye bye.
Bye.